Okay, there are three types of relationship between a line and a plane. Okay, so for the first one, like I said earlier, that it's possible that the line L would lie on the plane. Okay, so if the line L lies on the plane, basically, if you imagine that you have a plane, right, and this is exactly the plane will be P. Okay, and the line L right actually lies on the plane. The line L actually lies on the plane. Okay, what does this mean? So remember the line L does have its own direction, right? We may have own direction vector which is M. The plane also has another direction vector which is actually N. Okay, this really means that there's also the point L, right, also has another point A, correct, marked by the position vector A, right, so back from the origin O, like this is maybe point A, I just call it point A, and then the vector, position vector is A, twiddle, okay. Equation of line R should be R equals to A plus lambda M, where lambda is real, and the equation of the plane should be R, so called N equals to D. Okay, so how do we determine the relationship between a line and a plane? Okay, so first time you notice, right, we always take, like I told you in lecture, we always check that the m dot n, we always check the relationship between the direction vector and the normal vector. Okay, so meaning we check the relationship between the direction vector and the normal vector to see what it gives us. Okay, so first, right, if you look at this, right, number one, right, for this case, right, m dot n should be equal to 0. Agree? Right, so one lies on the plane, the other one is the normal vector to the plane. The relationship is that they are perpendicular to each other. So because you know that m is actually is perpendicular to n, correct? Secondly, how next I can see that if point A, right, actually lies on the plane, right? So you can see that point A lies on the plane. What does it mean? It really means that it lies on the. So you remember our plane is basically r dot n equals to d, right? Where this n here, r represents basically the position vector of any point on the plane. This r actually takes the form of basically like x, y, z. So actually a, right, is a point on the plane. Okay, so this a here, right, actually is a point of the plane. That means this position vector of any point, this can be a, right? This can be a, this can be point A. Okay, this can be point A. So that means I check, right? What I can check is if I sub a in as n, okay, equals to d, and if it satisfy, right? If satisfy, it means that actually the line lies on the plane. Okay, so if a lies on the plane, right? Okay, if a satisfy the equation of the plane, we can say that the whole line, right, lies on the plane. Okay, so the direction vector is perpendicular to normal. The point A fulfills the equation of the plane. Okay, so from here we can straight away conclude if the two conditions are met, right, line L actually lies on the plane. And not only that, I mean, you can actually conclude that there are infinitely, because let me go to case 2. Okay, so let me go to case 2. Case 2 is that line L, the case 2, right, is that could be so-called line L is parallel to the plane, but does not lie on the plane, but not on P. Okay, so example, it may be something like that. This is your line L, which is so-called R equals to A plus lambda M. Okay, the other one is N, normal vector. This is your normal vector. Okay, this is the plane. Okay, so one way you can see is, okay, of course, definitely if they are parallel, right? If they are parallel, it's so-called parallel to the plane, then you can also say that straight away m dot n is equal to 0. Okay, and you check that point A, right, there's actually this point A, remember, marked by position vector A. Check that this A dot n is not equals to D. So this means that the point A does not satisfy the equation of P. This means that A does not satisfy or does not lie on the P now, does not satisfy the equation of D. Okay? Then if that's the case, right, it just means that they are parallel. It just means that line L is parallel to P, but there is no point intersection. But there is no point of intersection. Okay, so next one would be case 3. Case 3, right? For case 3, straight away, example, this could be the plane, this could be the line. So if it's not parallel, it's not lying on, then line L could be intersecting with P. Okay, so very easy. You check away. First thing we do is always check if m dot n is equal to 0. So first, you can see m dot n will not be equal to 0 because the direction vector of the line is not perpendicular to the normal vector of the plane. So once you see that for all three cases, right, the first thing we do is always check whether m dot n is equal to 0. M dot n equals to 0, then check if the A satisfy equation. So if m dot n not equal to 0, straight away we can see that, basically they are intersecting. This is for case 3. Okay.